Okay, one more reaction of an epoxide. This one is called acid catalyzed ring opening reaction. Ring opening is still the same thing. That's all epoxide do. They open the ring. But the reaction one, the one we saw earlier, that's with strong nucleophile that go SN2. This one is used acid as a catalyst. Okay, so we have hydrohalic acid, so bromine chloride iodide. We have water, we have alcohol. But one thing you should see is that X, which is going to be nucleophile, water, nucleophile, and alcohol, which is also a nucleophile. They all attached to the more substitute carbon. The more substitute carbon. All right, what happened? Let's take a look at the mechanism. So, first of all, add an acid, so new protonation, and this guy going to be really, really unstable. So the three-membered ring also unstable already. Add proton on the oxygen, become positively charged. Even more unstable. The ring really want to be burst out. Right? Water comes in, burst out the ring, so attack at the more substitute carbon. Okay, so you get this compound, and then deprotonation. All right. Now, why does the nucleophile go to the more substitute carbon? Let's talk about it real quick. Okay. So if it were to be a primary and secondary carbon, they are competing. Right, steric hindrance, of course, take it. Two sterically hindered at the secondary position, so the X can go attack at the primary. All right, so this primary and secondary totally go attack primary. But if you see a tertiary, this is in acidic solution, not in basic. These are not strong nucleophile. Okay, so all these are in acidic solution. You got a positive charge on oxygen. All right, now. Tertiary versus primary or secondary, X gonna attack the more substitute carbon. Here's what happened though. There are two effects competing. Always have two effects competing. This one right here, so steric hindrance say, no, don't go attack that. Go attack right here. This is wide open. But there's an electronic effect on here. Let's take a look at electronic effect. Okay, similar to carbocation. So in an acidic solution, the oxygen is positively charged. Right, and oxygen by itself is already electron withdrawing, high electronegativity. Right now, we're gonna charge super high electron withdrawing. Right, that makes two carbon down here of the epoxide partial positive. Since both of them are partial positive, but they are not equal. One of them are more positive than the other. Right, in the solution, we can draw kind of resonance. It's not really a resonance, but you kind of be able to draw the resonance right here, left and right, with positive charge on the more substitute carbon and the positive charge on the less substitute carbon. Okay, both are positive, but one of them is more positive than the other, and here's the reason why. The more substitute carbon is more positive because this guy stabilizes the positive charge better than the other side. Okay, just like carbocation, more tertiary carbocation is more stable than primary, right? More substitute carbon can stabilize the partial charge better than the less substitute carbon. That's the reason why carbon right here become more positive, and CO bond right on the left on the more substitute carbon are weaker than the other side, right? So with nucleophile comes in and attack right there. All right, summarize what's going on in here. So go back right here. Oops, go back right here. So primary and secondary steric effect. So there are two effects competing: steric effect and electronic effect. Right? For primary versus secondary, steric effect dominates. So they said now this is two sterically hindered attack right here. Of course, this guy have more positive character, right? But steric effect dominates. So nucleophile will attack right here. But when you go up to tertiary, electronic effect dominates. So although right here is wide open, nucleophile will love to come here. But this guy is much more positive than the other side. And electronic effect in this case dominates the steric effect. So the nucleophile will attack right here. Okay. All right, let's try this together here. So. All right, so this one we add an alcohol. So which carbon will this alcohol attack? Tertiary, secondary. We go on tertiary, okay? Because this is an acidic solution. So oxygen, this oxygen gonna be partial positive, all right? So this it makes electron withdrawing. So carbon will be positive. Who's more positive? This guy right here, all right? So alcohol gonna attack right there. All right. So first of all, this is going to be a backside attack because the epoxide ring block anything that's coming from the front. Right? It's going to be come from behind. Okay. All right. I want you to focus on the stereochemistry of this methyl group. This alcohol going to go backside attack, and will push everything forward. Right. So burst out the ring, and methyl right here get pushed forward. And you're going to get methyl at the front, and the alcohol, incoming alcohol, going to come from the back. So it's kind of SN2 process. Okay. All right. So let's guess the product. All right. So first one, no acid. There's no acid here. This is strong nucleophile. And what does strong nucleophile do? Backside attack. Right. SN2 backside attack. Go right there. The let's substitute carbon. So you should get sulfide attack from behind. So on the dash. Okay. Next one, we add sulfuric acid. So this is acidic solution. The oxygen gonna be partial positive, gonna be electropositive. All right, makes these two carbon also partial positive. Who's more positive? The more substitute one. So the isopropyl alcohol will attack right there. All right, and when it attacks, so it's gonna come from behind. The alcohol gonna be on the dash line. And methyl, who's already on the dash line, we go to wedge right there. Push it forward. Okay? No, inverted, basically. Last one, what we got here, so HBr. All right, the first step, that's going to be protonation. So you should get the positively charged oxygen, and this guy ready to do reaction, right? Bromine going to go attack, so we have primary and secondary. So in this case, the steric hindrance dominant electronic effect. This, of course, this guy positive, but not positive enough to convince the nucleophile to attack right here. Yeah? So in this case, bromine gonna go attack right there. Okay, so you should get that. Stereochemistry stay the same because this carbon is not a reaction center. All right, so the example should clear up your question in a little bit. All right, okay. All right, let's do this together on the next video.